Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 9. It's on mass spectrometry, which is a way that we can separate atoms, isotopes, even fragments of molecules based on their mass. And so it's an incredibly effective machine. But before we get to the specifics of that, I want to talk a little bit about John Dalton. John Dalton was one of the pioneers of modern chemistry, and he was presenting at a conference in 1803 when he put forward his Dalton's atomic theory. And so let me go through that. And what I want you to think about is which of these have we changed over the last 200 plus years? He believed, number one, that elements are made of extremely small particles called atoms. He believed that atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. He believed that atoms cannot be subdivided, created, or destroyed. He believed that atoms of different elements combine in simple whole number ratios to form chemical compounds. And then number 5, in chemical reactions, atoms are combined, separated, or rearranged. And so over the last 200 plus centuries, if we were to look at those 5 things he put forward, there's really only 2 errors that I can find. Number 1, are all elements or all atoms of the same element going to have the same exact mass? No, remember they're going to be isotopes. Those are going to be the same the same element, but they're going to vary in the number of neutrons that they have. And then the other one is that we can subdivide atoms. So when we're looking at fusion or fission, but those really lay outside of normal chemistry. And so he did an incredible job. And what we're really going to focus on in this video is number 2, identification of isotopes. And so mass spectrometry is a way that we can modify Dalton's atomic theory, and we did that through the identification of isotopes, and that's around the early part of the 1900s. Isotopes, remember, are going to be the same element, but they're going to have a different mass, and that's based on the number of neutrons that they have. And what we can do from that is we can eventually calculate the average atomic mass, and that's going to be on the periodic table. It's sometimes referred to as the atomic weight. Now, also mass spectrometry can be used to look at individual atoms, elements in a sample, and we can even break apart big macromolecules and look at the fragments that are found within that, or molecules within it. And so if we look at a basic mass spectroscope, what we're going to see are 3 parts. We're going to have an ionizer, a mass analyzer, and then a detector. And so let's look inside the ionizer. What are we going to find? Well, the first thing we're going to find is it's a total vacuum. In other words, this doesn't work unless we remove all of the gas particles that are found inside the mass spec. Next thing we're going to do is we're going to insert our sample in. That could be a solid, it could be a liquid, it could be a gas, but we're going to inject it into this ionizing tube, and then we're going to hit it with electrons. And so we're going to move electrons through the sample. And so there's a little cathode ray tube. It produces all these electrons. And what it's going to do is it's going to pull electrons away from the sample. And then as it does that, it's going to create a number of positive ions. And so we're going to ionize that sample inside here. Remember, it's still the sample, it's just ionized. It's lost its electrons. And so now we move to the mass analyzer. That's really only going to have 2 parts in it. It's going to have an electrical field. You can see that's negative because we want to move the ions into the mass analyzer. And then we're going to have a magnet. And what that magnet is going to do is it's going to bend the path of the ions. And so as we're bending the path of the ions, it's just like driving around a corner. If you're really heavy, it's harder for you to make a corner. Let's say if you're in a big semi-truck. But if you're in a little motorcycle, it's easier to make it. And so this is where we're going to figure out the difference between the mass of those ions. And then finally, we have a detector. That detector is going to be made up of 2 things. We're going to have an electron multiplier, which is essentially a plate. As electron hits it, it spawns more electrons, which hit the next plate, which spawns more electrons. And so we can really have a small amount of ions or anything hitting that plate, and we're going to get a signal. Now that signal has to be amplified, but eventually we can send that into a computer and we can look at the spectrum coming from those different masses. And so the first thing you have to do is you have to calibrate the machine. What does that mean? You're going to start sending ions through. Okay, so that ion didn't hit the detector. Why is that? It's because the magnet is turned up too high. And so we're going to have to lower the strength of that electromagnet. We run another ion. Okay, now the magnet's not quite strong enough. And so now we run another ion, another ion, another ion. Okay, so we've calibrated it, and so it seems like it's working well. Which of these would be heavier? Well, the ones that are heavier are going to be the ones that can't quite make the corner, and so they're going to end up out here, and then the lighter ions are going to end up right here. Now let's actually get to some sampling. And so this is what it's going to look like when we create a spectrum. We're going to have the different weights across the bottom, and then we're going to have the intensity. And so wherever the intensity is high, we're going to have peaks. That means we have a lot of ions that are with that specific atomic weight. And let's try chlorine. So we're going to put chlorine through here. Chlorine really only has 2 stable isotopes. It's going to have chlorine 35 and 37. And so let's watch and see what happens as we send this chlorine through the mass spec. Okay, so what did we find? Well, there's really only 2 types of ions, and so we're having 2 peaks. Which one is going to be the chlorine 37? Which one's going to be the heavier ion? Well, that's going to be this one right here because it wasn't bent as much using that magnet. If we look back at that, let's look at those ions flow again. So you can see the chlorine 37 doesn't quite make it around the corner. And which do we have more of? Well, we're going to have more of that those with an atomic mass of 35. Okay, so once we've got that, we can really figure out this average atomic mass. And so how do we figure that out? Well, I'm using values right here that I grabbed from Wikipedia. So here are going to be the 2 stable isotopes that we have of chlorine. Here's going to be their mass, their actual mass. So that's based on the number of protons, neutrons, and electrons inside it. And then this is going to be their abundance. In other words, it's around 75% of chlorine 35 and around 25% of chlorine 37. And that's why this peak is going to be 3 times the height of this peak if you're looking at a spectrum. So how do we figure that out? Well, that average atomic mass, sometimes referred to as the atomic weight, is simply going to be the mass times the abundance plus the mass times the abundance. And so in this case, since we only have 2 isotopes, we're just going to only have 2 values here. But if we had a lot of isotopes, we're just going to have more mass times abundance. We just add on like that. So let's throw in the values here. So we've got mass A, which is going to be 34.97. And we're going to take that times its abundance, which is around 75%. We then take the other isotope, which is chlorine 37, and times its abundance. And what we get is 35.45. And that's what's going to be on the periodic table. And so when you're looking at those values on the periodic table, what you're looking at is the average atomic mass. And they figured that out by looking at the natural abundance. Okay, now what's important is a mass spec can be used for other things. Not only for atoms and isotopes within individual, or isotopes within an individual element, but we could look at atoms within a molecule, and we can even look at fragments within macromolecules. And this right here is myoglobin, which is a massive protein, and what we can do is we can send it through a mass spec, and what we can figure out is all the amino acids that are found within it. And so remember, wherever the peaks are going to be a little bit higher, then we're going to have more of that amino acid. And so usually what they measure this is M to Z, which is like a mass to charge ratio. And so did you learn this? How to use data from mass spectrometry to identify elements and mass of individual atoms in an element? Remember, it all ends up on that curve. And if you can make the curve or not is going to be based on your mass. We can look at a spectrum from that to figure out their abundance, and I hope that was helpful.